Well, let's get started. So we'll do a problem. So this is from a review from this past semester. We're given the following. The line y equals 5 minus 2x is tangent to y equals f of x at x equals 1. The line y equals 3x minus 4 is tangent to y equals g of x at x equals 2. And the point 2, comma 1 is on this curve f of y quantity squared plus g of x quantity squared equals 4xy plus d. And the question is, determine the constant d and find the tangent line to the curve at the point 2, 1. So this combines a lot of ideas. And you might say, does it really combine something we talked about last time? Well, it does in the following sense. If you look at this relationship here, this is going to be an implicit relationship. I can't solve for y as a function of x. In fact, I have a huge obstacle, and I don't even know what f is. So it's kind of hopeless to try to solve for y as a function of x. So it's an implicit function. So if I want to find a tangent line, well, to find a tangent line, I'm going to need to get a slope, which means I'm going to have to take a derivative. So this is a problem that involves implicit differentiation. Now the good news is we do have a point 2, comma 1. All right, so that means that when we do part B to find the tangent line, well, it shouldn't be too bad. Now, before we jump into doing the problem, we should do what we do whenever we see problems where it says, we're given a tangent line. Because given tangent lines is really secret code for saying something is happening. So for the first line, y equals 5 minus 2x is tangent to y equals f of x at x equals 1. So that tells us we know two things about f. Namely, what happens at 1 and what happens to the derivative at 1. Now to find f of 1, we plug 1 into here. 5 minus 2 times 1, well, that's 5 minus 2, that's 3. To find f prime of 1, we look at the slope. So the slope is negative 2. So that's what we know about f. We know that f of 1 equals 3, f prime of 1 equals negative 2. Then there's another part that says, hey, we have this second line. This line y equals 3x minus 4, which is tangent to g of x at x equals 2. So what does that tell us? Well, it tells us we know a little bit about g. So we know what g of 2 will be, and we know what g prime of 2 will be. And we say, okay, to find g of 2, plug 2 into the line. Let's see, we're going to get 6 minus 4, which is 2. For g prime of 2, read off the slope, which is 3. So we start by saying we know stuff about f and g, namely we know that information, and that's good for us. Now we're ready to start answering the question. So for part A, it says, hey, what's this d? All right, well, how do we find it? Well, we want to plug in x equals 2, y equals 1. So we do that. So we would have f of 1 squared plus g of 2 squared equal to 4 times 2 times 1 plus d. All right, well, hopefully we know what these things are. Do we know f of 1? Yeah, we do. It's 3. So 3 squared plus g of 2, yeah, it's 2. 2 squared is equal to 4 times 2 times 1, which is 8, plus d. So that's 9 plus 4, which is 13. Subtract 8, and we see, aha, d should be 5. So if we choose d to be 5, then we're going to have the point 2, 1 is going to be on the curve. Because we verified it. We plugged in 2, comma 1. And we saw what we needed. So that's part A. That's the non-calculus part. Now for the calculus part. Well, we said we're looking for the tangent line. We already have our point, so it comes down to our slope. So we're going to start with our equation. F of y, whoops, there we go, f of y squared plus g of x squared equals 4xy plus 5. And implicit differentiation works by saying, just take the derivative of everything on both sides with respect to your variable. Now, in our case, we're looking for the slope of the tangent line. So that means what we need to do is we need to find dy dx. The x downstairs, that says, what do you take the derivative with respect to? So we're taking it with respect to x. So we say, all right, take the derivative with respect to x, and we go through. And here we're going to need to use the chain rule. So the derivative of f of y quantity squared, well, that's 2 f of y to the 1 times the derivative of f of y, which is f prime of y. And are we done? No, because we keep going. Times the derivative of y with respect to x. And the derivative of y with respect to x is the derivative of y with respect to x. Plus, then similar thing, be 2 g of x to the 1 times g prime of x. And then you say, well, don't we need to take the derivative of the inside? Well, we could. The inside is x. Derivative of x with respect to x is 1. All right, equals. On the other side, we use the product rule. Derivative of x is 1, so we'll get 4y, then plus 4x, times the derivative of y with respect to x, which is dy dx, and the derivative of 5 is 0. So, okay. Took the derivative of both sides with respect to x, and then we remembered our cardinal rule. And we should have probably stated this before we took any derivative, which is to say, aha, anytime when I look at y in implicit differentiation, I'm always really going to think of it as y as a function of x. So here we are, we're just thinking in our mind, this is what's true. And you can tell we're thinking because we're scratching our heads, thinking, this is going to be fun. Of course, we're doing math, so we've got to put a smile. So, okay. So that's how we do these implicit differentiation problems. Y is a function of x. Now, are we done? No. We need a number. We need a number. Our slope should be a number. So, we should evaluate. Now, there's two things. You can either solve for dy dx, then plug in, or plug in and then solve for dy dx. Usually, the sooner you evaluate, the less likely you are to make a mistake. So here we go. We'll have 2 times f at 1, because y is 1, times f prime of 1, times dy dx, plus 2 times g of 2, g prime of 2, again, x is 2, is equal to 4 times 1, plus 4 times 2, dy dx. Well, f of 1 is 3, and f prime of 1 is negative 2. G of 2 is 2, g prime of 2 is 3. So we're going to get 2 times 3 times negative 2, which is minus 12, dy dx, plus 2 times 2 times 3, which is plus 12, is going to equal 4, plus 8, dy dx. So we move stuff around, and we'll get that 20 dy dx, because you're going to add 12 over, is equal to 12 minus 4 is 8. So dy dx, that's 8 over 20. Well, both things are divisible by 4, 2 over 5. So that's our slope. Now, are we done? Not yet, because you always have to remember what the problem asks for. In our case, it says find the tangent line. So our final answer is y minus our y value is equal to our slope, 2/5 x minus our x value. And now we really are done, because we found our line. Good. Well, that's fun. Hopefully we'll have another fun one on the exam. We can always hope. So what's our goal for today? Our goal for today is we're going to talk about inverse functions. In fact, there's a couple of things we're going to do today. It's a very fun day. So let's remember how inverse functions work geometrically. So the idea is suppose I have a function y equals f of x, and this is a blue function here, up here. Now, if I want to get the inverse function, one of the ways you often do this in algebra is you say, oh, let's swap x and y. So an intermediate step is to say x equals f of y, and then you solve. Now, in terms of the picture, when you swap x and y, it has the effect of flipping across the line y equals x. So you took your blue curve, you flipped it across the line y equals x, and you end up producing this new curve, this red curve. And this is the inverse function of x. So, what is our goal? Well, our goal is to take derivatives. Now, we're going to make an observation here. It's actually right there. The tangent lines will flip. So that is to say, suppose I say, I'll pick this point here. If I look at this tangent line, well, what does it look like? It looks like y equals mx plus b for some choice of m and b. Well, what happens is when I flip my curve, I can also have the tangent line come along for the ride. And what it'll do is it'll end up over here. And this is another line. Well, what line? X equals my plus b. Because remember that to get inverses, what do? You swap x and y. Okay, so I say, aha, there's a nice relationship between tangent lines to the original function and tangent lines to the inverse function. Well, that's pretty good. So that's what we have. In fact, that's sort of the observation here. If I have a point, and so this is my point here, this is a, f at a. Well, what's the point? Down here. Well, you swap x and y. It's f of a comma a. So that's what happens. All right. Well, we said x equals my plus b. You rewrite it. Y equals 1 over m times x minus b. So you can solve for y. So that tells us a lot. It gives us information. And in particular, it says, hey, if I want to know this slope of the tangent to the inverse, I figure out what's the point over here that it should match with, find that slope, and then I'm going to flip. Because notice the slopes, how they relate. M versus 1 over m. So if I can just find the right slope, I just flip it up, and I'm done. And I'm done. So what's the right point? Well, turns out it's not too hard to figure out. It's the following. If I want to take the derivative of f inverse at any value of x, what do? Well, it's 1 over, and that's 1 over is coming from over here, the derivative of the original function, but I have to be careful. I don't evaluate it just anywhere. I have to evaluate at the right corresponding point, f inverse of x. So it's just saying, I have to take 1 over, but I have to move to the correct location. So that's the geometric way to derive this formula. The derivative of f inverse of x is 1 over f prime of f inverse of x. And you'll notice there's a box, which means you should know this formula, because it might be useful at some point in the future. All right, so remember the formula. Remember the formula. Well, suppose you don't want to remember it. You can always rederive it. If you don't like to do it geometrically, we can also do it using the implicit function theorem. Sorry, the implicit function approach. What's the implicit function approach? Well, here we go. And we're going to use this multiple times today, so it's good to know it. So we start by saying, all right, I want to understand y equals f inverse of x. But I don't understand f inverse. So we say, that's okay. Just think about it as f of y equals x. Because saying that y equals f inverse of x is equivalent to talking about f of y equals x. That's the way that inverse functions work. Well, now let's take the derivative of both sides. Now, some things are much easier to take than others. If I'm looking at these two derivatives, I would say, hey, the derivative of x, I know that one. It's 1. How do you take the derivative of f of y? It's the chain rule. So it turns out it's f prime of y times the derivative of the inside, which is dy dx. And now we're almost there. So dy dx is 1 over f prime of y. But it's kind of unsatisfying, this answer, because we really want to end up with something just involving x. And so I say, all right, how can I replace y? Well, I go back to the very first line. And I say, wait a second, y is f inverse of x. So I can substitute. And therefore, the derivative of f inverse of x is 1 over f prime times f inverse of x. So this is a way to take implicit, or rather to use implicit functions to take derivatives. So let's try an example. Suppose that we're given that f of x is x cubed plus 4x plus 5. And g of x is f inverse of x. And we're asked, find the tangent line to y equals g of x at x equals 10. Now, it turns out that this function, and we won't prove this today, but we can prove this in a week or so, it looks something like that. It is actually a nice invertible function. Now, could we find the inverse? Do we have the tools to say, oh, we swap x and y and solve for y? Is it possible? Well, technically, yes. There is a formula to solve cubics. However, it's a very long formula. So if the formula for quadratics is, say, this long, the formula for cubics is that long. It's a very long formula. We don't know it. You probably have never seen it. So we're not going to do that. We're going to try to use a better way. Namely, we're going to use the theory. All right. Well, what are we after? We need to find the tangent line. So if we're going to find the tangent line, what two things do we need? Slope and point. Okay. Let's talk about our point. Do we know our point? Well, where's our point? We know the x-coordinate. So our point would be at 10, comma, g of 10. Well, that's unsatisfying. We need to know what is g of 10. So we say, well, what is g of 10? By definition, that would be 10 f inverse of 10, because g of x is f inverse of x. So I need to find f inverse of 10. Now, I just gave a big long rant that said we're not going to be able to solve for the inverse function. And now I'm coming here and saying, well, we need to find the inverse at 10. Well, it's good news, though, because this says you don't have to find the whole function. All we have to do is figure out one time when x cubed plus 4x plus 5 produces 10. So to find the f inverse of 10 says, when does an x value into our function produce an output of 10? So if I can find any x where this is true, then I'm good to go. So we come down and say, this is what we have to figure out. Now, if you see this type of situation, what's a good method to start with? What's a good method to start with? The answer is you guess. Now you're probably thinking, that does not sound very mathematical, guessing. But actually, guessing is a wonderful tool in mathematics. And when you get to differential equations, you're going to discover that about half of the techniques are, well, make a guess. And then like, okay, you're wrong, but here's how to improve it to get the right answer. So guessing is really useful. And it's always something you should think about. Can I guess the answer? So looking at this, is there a nice value to try? So you should have like a small set of numbers to work with. 0 is a good one because it's easy to check. 0 would give 5 equals 10. That doesn't work. Someone said 1. 1 plus 4 plus 5. Equals 10. Yes, we're done. X equals 1, and we move on, and we don't question anything else. So we were able to guess the solution. Okay, so that means that our point is going to end up being at 10, 1. Now, we're not done because we need our slope. Okay, so how do we do our slope? Well, for our slope, we need to find g prime at 10. Because I need to find the derivative of the function at 10. So, the derivative of g is the derivative of f inverse of x. So according to the formula, it says 1 over f prime of f inverse of 10. So using the formula here, with x equals 10. But we just figured out what f inverse of 10 is. What is f inverse of 10? It's 1. So 1 over f prime at 1. So now we have to find out what is f prime of 1. Well, let's do a little side work here. What is f prime of x? 3x squared plus 4. So f prime of 1 would be 3 plus 4, which is 7. So g prime at 10 is 1 over f prime of 1, so that's 1 over 7. Now we're almost there. So we have our point, 10 comma 1. We have our slope, 1 over 7. So our final answer is that y minus 1, our y value, is equal to our slope, 1 over 7, times x minus our x value, 10. And that's it. Good. Okay, that's not so bad. So there's one really useful function that we haven't quite mastered the derivative of. So we're going to talk about the logarithm. So here we go. Let's talk about the exponential functions and logarithms. So we're going to go through a whole bunch of properties here. So we'll start off very simply that the exponential functions and logarithms are related in the following sense. The logarithm is the inverse function of the exponential function. So y equals e to the x, if you graph that, which, well, we can graph that. We know how to graph y equals e to the x. That looks like this. Well, if you then were to flip it across the line y equals x, you'll get the function that looks like that. This is the log function, log x. So these are inverse functions of each other, which means that there's lots of wonderful properties that connect them together. As an example, when you multiply two things that are in the exponent, e to the a times e to the b, you add the exponents together. That's e to the a plus b. This translates into logarithms as log of a times b is log of a plus log of b. This is one of the reasons, by the way, why logarithms are so cool. They transform multiplication into addition. And addition is easier for us to do. Well, that's not the only thing that's true. If I take e to the a and I raise it to the bth power, that's the same as taking e raised to the power of a times b. So in other words, these exponents multiply. That translates into logarithms as log of a to the power b is b times log of a. Another amazing fact. If I do division, e to the a over e to the b, that's subtraction, which in log says division becomes subtraction. You can get that from combining the previous two facts together. And of course, the fact that there are inverses, log of e to the x is x. E to the log of x is also x, but of course, x has to be positive. If you think about the graph y equals log x, it's only defined for positive values of x. And a few more facts. We're almost to the end of our facts of logs. E to the 1, it turns out, true story, is e, which says that the natural log of the number e is 1. And e to the 0 is 1, which tells us that the natural log of 1 is 0. And now, the cool fact. If you think about y, and you say y equals log x, then x equals e to the y. That was one of our very first things we set up here. Take implicit differentiation on both sides. Then you'll get that 1 is equal to e to the y times y prime. But we say, hey, wait a second, e to the y, by definition, is x. So 1 equals x times y prime. And if you rearrange it, we get to the conclusion. The derivative of natural log of x is 1 over x. And there you go. There you go. Now, I will say that there's generally a bigger statement there's the following is actually true, which is if you take the derivative of natural log of absolute value of x, it's still 1 over x. Because as we write it like this, there's no absolute values, which means we should only be plugging in positive numbers. We're not going to be very strict about that. Just remember that if you ever need to, you can deal with negatives. Throw absolute values in. Life is okay. Now, we're going to use this so much that it's good to remember the following fact. If I take the derivative of log of f of x, well, I can apply the chain rule, and I can say that's 1 over f of x times the derivative of f of x, which is f prime of x. So you will use log. This one should be so instinctive, you shouldn't even think about it. You see the derivative of log of something, you say, okay, well, the derivative of log is 1 over, that's what this says downstairs, but then it's 1 over the inside by the chain rule, then times the derivative of the inside. So let's take some derivatives here. Log of secant of x. What does that become? What's the rule? Well, 1 over the inside, which is secant of x, times the derivative of the inside, which is secant times tangent. And what do you notice? Secants cancel out. You just end up with tangent. Now that's kind of nice. Probably wouldn't have guessed that if you take the log of secant and take its derivative, you'd end up with tangent. Huh, interesting. Okay, let's take the derivative of log of x to the 100th power. All right. Well, what's the rule? Well, 1 over the inside, x to the 100, times the derivative of the inside. Well, what's the derivative of x to the 100? 100 x to the 99. But notice there's a whole bunch of x's. We could cancel them out. If we cancel them out, what are we left with? 100 and there's a single x. Is it upstairs or downstairs? A single x downstairs. Huh. What if we did the derivative of 100 times log of x? What would that be? Well, now we don't even have to do any fancy stuff at all. 100 is a constant, and the derivative of log x is right there. 1 over x, which is also 100 over x. Wait a second, that's the same thing as that we just did. Coincidence? No, it's not a coincidence. Well, why not? Well, notice how do these two things relate? They're the same thing, because there's this nice rule that says I can bring exponents down in front. So I could simplify my expression before I took the derivative. And that's a nice idea to know. And we're going to use that idea in a few minutes. Okay, well, we're almost getting there. How about the derivative of log of x cubed minus 3x plus 2? What would that be? Well, the rule says 1 over the inside, x cubed minus 3x plus 2, times, by what? Yeah, 3x squared minus 3. All right, is that the answer? Yeah, sure, that works. Could you simplify it further? You could. It turns out, if you stare at this for a little bit, you'll see that x equals 1 is a factor for upstairs. It also works for downstairs, which means you could factor stuff out, but we don't have to. We weren't asked to do that. Okay, one more. This one's the fun one. All right, if you haven't seen this before, what could it be? The derivative of natural log of secant x plus tangent x. I suppose I should have pointed out on the previous slide, we didn't say, oh, natural log of x cubed and minus 3 natural log of x plus natural log of 2. And there's a reason we didn't do that. because natural logs are great for great for multiplication. They're great for powers, but they suck, for lack of a better word. Absolutely do not mix at all with addition. Logs are not built for addition. If you see a log in addition, you're like, oh, darn it, that's no good. All right, now back to this one. Log of secant plus tangent. Well, 1 over secant plus tangent. Okay, that's fine. What's the derivative of secant? Okay, secant times tangent. What's the derivative of tangent? Secant squared. Now here we will simplify. Notice, what do the upstairs have in common? We both have secant, right? So I could factor it out. Secant x times tangent x plus secant x. Now, I factored that out. Now what do you notice? They both have secant plus tangent. There's one downstairs, there's one upstairs. We changed the order, but the order doesn't matter when we're talking about addition. So that cancels. So what are we left with? Secant. Wow. Now that one is really unexpected. Log of secant plus tangent, take its derivative. You get secant. Who knew? Who knew? Okay. So now we can do a couple of other fun things. We've talked about the derivative of e to the x. We can also take the derivative of a to the x, where a is any number we want. And this really doesn't require any facts of what we talked about today. So how do you take the derivative of a to the x? Well, it turns out that a is e to the log of a. Now, if you're wondering how do we know that, well, that's actually the fact from here. E to the log, in our case, a is equal to a. Okay, so I can replace a by e to the power log of a. Then e to the log of a to the x is the same as e to the log of a times x. And now we use the chain rule. So the derivative of e to something is e to that something times the derivative of something, so that's why the log of a comes down. And then we say, aha, that e to log a of x, if you just worked backwards, that was the same as a to the x. All right, so when we're taking the derivative of a to a power, just remember, multiply by a log of a at the end. Now the nice thing is log of e is 1, so it's consistent with the rule we've talked about before. So let's try something. What's the derivative of x to the power x? Now, the weird thing is, x is playing two roles. See, it's downstairs. So we're like, well, maybe we should think of it in the sense that if we think of x as being that downstairs part, the base, then we have this rule that says the derivative of x to the k, well, that's k times x to the power k minus 1. In this case here, k would be x. So it would be x times x to the power x minus 1. Now that's if that's how we chose to think of x, as being the bottom part, the base. But x is also upstairs, which means we could think of it as being the exponent. So then I have the derivative of a to the x. And we say, well, we just did that. Just right there. Which would mean that if we apply that and we think of the bottom x as being a fixed thing, we'd have x to the x, which is the sort of the a to the x times log of a, log x. Well, now which one of these is the right idea? So, should we use the first idea where we think of it as being the base? No, not very many takers on that one. Okay, should we think of x as being in the exponent? No? No takers at all? Okay. All right, should we use neither of these rules? Okay. All right, we have like 3 or 4 people. All right. Should we go with the fourth option? Okay, there's a lot of people not voting here. That's not how it works. Well, the answer is we're going to go with the fourth option. And you might say, what is the fourth option? Fourth option is we're actually going to use both, which doesn't sound right. But let's figure out what happens. So if I want to take the derivative of x to the x, I say, look, I can't use it in this form. I don't know a rule that applies. So I'm going to think of a way to rewrite it so I can use a rule. So an easy way to rewrite it is to do something as what happened over here, where we said, well, a, we replace it with e to the log a. So we're going to do it that x becomes e to the log of x. All right. Well, why is that useful? Well, we can keep going and say, well, now this is the derivative of x, derivative of e to the power x log x, because I can multiply these two together. Now, x to the x we don't know how to handle yet, but x times log of x we do know how to handle. By what rule? The product rule. So we now have things we can handle. So we apply our rules. So first we have the chain rule. Derivative of e to a something is e to the something. So x log of x times the derivative of the upstairs. So that's e to the x log of x. The derivative of x times natural log of x, well, I'd have x times the derivative of log of x, which is 1 over x, plus the derivative of x, which is 1, times natural log of x. Now, what can we do with this e to the x log of x? That is just another way of writing what we started with. So that would be x to the x. Now, if we multiply that through to the two pieces, well, I have x to the x times 1 over x. And I'm going to choose to write this in the following way. I'm going to have this x here. X to the x times 1 over x, what does that become? It becomes x to the power x minus 1. So, because this 1 over x is like x to the negative 1. If I combine those two together, that's x to the power x minus 1. Plus, now when I go to the second term, I'll have log of x times x to the x. And if you look, you'll say, hey, they're both there. X times x to the power x minus 1. It's right there. And then on the other hand, log of x times x to the x is right there. So they ended up both being used in some sense. The reason they were both used was we sort of separated them, and when we took the product rule, we said, hey, treat one thing as being fixed, take the derivative of the other. So if we think of the exponent being fixed, that ends up being this rule. If we think of the base as being fixed, that ends up with that rule. So it actually is the case that we used both. All right. Well, what are some other things we can do? Well, now that we have the logarithm, we can do what's called logarithmic differentiation. And where the logarithmic differentiation comes from is the idea of saying, hey, we can use logs to simplify complicated expressions. In particular, logs have these two beautiful properties that say multiplication can pull apart. And if I have exponents, I can bring them down. So oftentimes, if we have a condensed expression where there's lots and lots of stuff multiplying and dividing in one term, if we take the log, it pulls it apart. So here's the idea of logarithmic differentiation. You take the logarithm. Now, use properties of logarithm to simplify. That's to pull it apart. And then you take the derivative of your small pieces. So how does this work? Well, here's sort of an idea. If I want to take the derivative of f of x, well, that's f prime of x. That's, okay, yeah, that's just notation. That's not a surprise. Well, imagine I could rewrite that as f of x times f prime of x over f of x. And again, you're like, well, of course, the f of x is cancel. But now it's the great, aha, we've seen f prime of x over f of x before. Do you remember where? Yeah, it showed up when we did the chain rule. Natural log of f of x is f prime of x over f of x. So, lo and behold, we get the following. That if I want to take the derivative of f of x, this is f of x times the derivative of log of f of x. All right. So how do we use it? Well, suppose I want to take the derivative of e to the x times x squared plus 1 to the cosine of x. What can we do? Well, this looks complicated, but it's a bunch of stuff multiplying and weird stuff in exponents. So I say this is geared for logarithms to make it easier. So we're going to think of this as our f of x. So according to the rule, this would be our original function, e to the x times x squared plus 1 to the cosine of x times the derivative of natural log of my original function. Now what we do is we say, okay, we're going to use our natural log power. So we took part 1, where there's a logarithm involved. So this e to the x in front term, x squared plus 1 to the cosine x, that's just going to follow us all the way through. So the derivative of, here we go, natural log of e to the x plus natural log x squared plus 1 to the cosine of x. Well, that wasn't too surprising. We just basically said, hey, there's multiplication going on with those two terms, pull it apart. But we keep going. E to the x, x squared plus 1 to the cosine of x. And, well, natural log of e to the x. What does that become? It becomes x, because natural log and e are inverse functions of each other. So that first term becomes x. Can we do anything with the second term? The cosine can come down. So now we don't have to worry about a power of something. No, it's a function, cosine of x, times log of x squared plus 1. So we've transformed the original problem of taking a derivative to the problem of taking this derivative. And you'll notice that the pieces are much simpler to work with and they're pulled apart. The more you can pull it apart, the easier it is to take the derivatives. So you end up with e to the x times x squared plus 1 to the cosine of x. And now take the derivative of the terms. Derivative of x, 1. Now come to here. Well, product rule. Derivative of cosine of x, negative sine. Then natural log of x squared plus 1. Then plus cosine of x times the derivative of natural log of x squared plus 1. Well, x squared plus 1 goes downstairs. What goes upstairs? The 2x, because it's 1 over the inside, so 1 over x squared plus 1, times the derivative of the inside, which is 2x. Now, at this stage, what do? You box it, because we're done. We were asked to find the derivative, and that's the derivative. That's about as simple as you can get. Now, I will say that the book tends to do logarithmic differentiation in a slightly different way. So let me just point out the difference from this and the book. So the book says, hey, you're asked to take this derivative. I don't know how to take that derivative. So I'm going to just call this function y for a few minutes. E to the x times x squared plus 1 to the cosine of x. And then I still want to take the log, so I'll still take the log of both sides. So you'll notice it's a lot of the same process. So you say, okay, I don't know how to take this derivative, but maybe taking the log will help simplify. That's what we did here. We said, transform it to taking a log. Now, this expands the same as it does before, x plus cosine of x, log of x squared plus 1. So take the derivative of both sides. What's the derivative of natural log of y? 1 over y times the derivative of the inside. The derivative of y with respect to x? dy dx. Okay, that equals, then you take the derivative of this other side, and again it's the same process in terms of taking the derivative, so we'll just note that that's our derivative. But what do we do? Well, to finish it off, we say that dy dx is equal to, multiply both sides by y. 1 minus sine of x log of x squared plus 1 plus cosine of x 2x over x squared plus 1. But the last thing is, I don't want to end up with a y. Everything has to be back in terms of x, and so you substitute back in. So everywhere you see a y, you replace it by the original function. So the derivative of y with respect to x is the derivative of the original function is equal to the original function, e to the x, x squared plus 1, cosine of x times this other part. So this is how the book does it. I personally prefer not to do it this way, but as long as you get the answer, you get the answer. Okay, well, we have a few minutes. Let's prove something useful. We're going to use properties of logarithmic differentiation to prove some nice facts. All right. What's the derivative of x to the k? Well, what did we say it was? Kx to the k minus 1. The problem was we didn't actually prove it for all values of k. We only proved it for special nice values of k. We're going to prove it for all values of k using logarithmic differentiation. So logarithmic differentiation says the derivative of x to the k is, well, according to here, the function, that's x to the k, times the derivative of natural log of x to the k. Well, what's another way to write natural log of x to the k? Yeah, the k can come down. Now k is a constant, so we get x to the k times the derivative of log of x, which is 1 over x, or if we combine these two powers of x together, kx to the power k minus 1. And that's the verification that derivative of x to k is kx to k minus 1 for all values of k, no matter how strange you get. I'm not done yet. I still have a minute. I'm going to get you paid for the full hour. You're going to get the full hour. Okay. One more. Okay, so here we go. Product rule. You can actually derive product rule from logarithmic differentiation. So how does that work? Well, if I want to take the derivative of f of x times g of x, I can use the rule here. So that's f of x, g of x, times the derivative of the log of f of x, g of x. But what can you do when you have a log of a product? You can pull it apart. So that's the derivative of the natural log of f of x plus the natural log of g of x. It's like, oh, hey, product rule has a plus in it. Interesting. In fact, we're going to see derivative of log of f of x. Well, that's f prime of x over f of x. The derivative of log of g of x is g prime of x over g of x. Now multiply through. The first term, the f of x is cancelled. So you get f prime of x times g of x. And then in the second term, the g of x is cancelled. So you get f of x times g prime of x. So logarithmic differentiation is a very fun tool, and it's definitely one you should know. Let's do one more example. Find the derivative of x cubed plus x, sine of x to the power x squared, and secant of x squared of x squared plus 4. And we're going to think of this, got to be careful sometimes with notation. So secant of x is separate. All right. Now you're probably thinking, hey, let's use logarithmic differentiation, which is natural because, hey, we just talked about logarithmic differentiation. But what if we hadn't just talked about logarithmic differentiation? What's the clue? Well, there's really two clues. Clue number one is when we see stuff with x raised to a power of stuff with x. It doesn't have to be the same stuff. Just in general, if we think x is both downstairs and upstairs, got to do logarithmic differentiation. No other way. But the other thing that clues us in is lots of multiplying and dividing. So if we have something with lots of multiplying and dividing, we're like, hey, logarithmic differentiation is really good, because it turns out that multiplication becomes addition, division becomes subtraction. What's happening is we're pulling the terms apart. And so when you pull it apart, the individual pieces are actually a lot easier to work with. And we like it when things are easier to work with. It's our favorite thing. So we begin. All right, so we're going to find this derivative. So if we do logarithmic differentiation, again, we're thinking this as, here's our f of x. So we would say that this is the derivative of f of x is f of x times the derivative of log of f of x. So that's logarithmic differentiation in a nice compact form. So, here we go. X cubed plus x sine of x to the power x squared over secant of x times x squared plus 4 square rooted. Write that in a calculus way, x squared plus 4 to the 1/2. There's our f of x, and we times it by the derivative of the natural log of all of this stuff. X cubed plus x sine of x to the power x squared, all divided by secant of x to the x squared plus 4 to the 1/2. So that's essentially step 1. Step 2, use your properties of logs. So x cubed plus x sine of x to the x squared. Yeah, there's a lot of writing on this problem, but that's okay. Just got to be careful we don't accidentally do things like, on this one say, ooh, that's still a 4, so make sure it keeps its 4-ness. So, what are the properties of logs? Okay, 3 things to remember. Multiplication becomes addition. Division becomes subtraction. And exponents come down. So, if you can remember that, you can do it in one step. If you have a hard time, just be careful. So, in one step, well, x cubed plus x is a term. There's no power, so that'll be one of our terms. Log of x cubed plus x. Next term, that's upstairs, sine of x to the x squared. Well, I have a power, so the power comes down. X squared log of sine of x. Now we go to the downstairs. That's our subtraction. Subtract log of secant of x. And now, again, another subtraction. And there's a half power, so the half comes down. Half log of x squared plus 4. And that's it. So we write the formula. We take logs and use properties of logs. We pull it apart. And now we take the derivative of each piece. So we still have this part up in front. It will always be there. A constant reminder that this is what we're taking the derivative of. That's okay. No problem. Nice for you to come along for the ride. And now, because, as you see, we've pulled it apart. Lots of addition and subtraction. Now, instead of having this complicated, convoluted expression, because you're like, well, I could almost do quotient rule here. Now, it's much simpler. Each little piece is not so bad. So, we work through it one at a time. Log of x cubed plus x. Well, when I'm taking a log, x cubed plus x goes downstairs, and the derivative of that goes upstairs. 3x squared plus 1. Plus x squared log of sine x, product rule. Derivative of the first, 2x, log of sine x, plus x squared times the derivative of sine x. Well, derivative of sine x, sine goes downstairs, and then derivative of sine goes upstairs. So that would be cosine of x. Minus log of secant. Secant goes downstairs, and the derivative of secant goes upstairs. Secant x, tangent x. Minus a half, that's the constant, x squared plus 4. X squared plus 4 goes downstairs, and 2x goes upstairs. And now, we could say we're done. And we are done. But we will do a few small things. There's a few small things we could do to simplify. We're not going to do too much. It definitely isn't worth multiplying this out. We won't gain any insight by multiplying it out. Still a 4. Don't forget about the 4-ness there. First term, that's about as simple as we can go, so we're fine with that. The second term, well, 2x log sine x. That looks pretty good to us, so we'll be happy. The next term, well, you get a cosine over sine, so we might as well throw it in, say it's a cotangent. The next term, the secants cancel, so we'll write that as tangent. And then here we can cancel off some 2's, so minus x over x squared plus 4. And there you go. There you go. So what's the big thing? Well, the big thing is really this step. That's the important step. Because what you're doing is you're saying, hey, I have a complicated thing, but I can break it down into a bunch of small, simple things. That's actually a good way to approach mathematics. Hey, here's this complicated problem. Can I break it down into a bunch of small, little problems that I can do? And if you can, that's a victory. Victory. All right. Well, keep practicing and have fun.